Yeah, good afternoon, everyone. Myself, Divyashree K, and I'm as application and design support engineer at Trident Infosol. I'm leading the application and design support engineer for the MBSC tools. I'm handling the DESO portfolio. So, welcome to the webinars on the topic System Engineering Future Ready. So, in the next 1 hour, I'll be taking you through the introduction on digital evolution in system engineering, and let me address some common challenges in system engineering that we are facing in the industry today, and followed with the digital transformation in SC. Then I have taken a case study of automatic headlight system where I'm addressing the challenges with the solution of modeling and simulation of AHL, then followed with requirement in loop simulation. Then finally, we are tracing all the artifacts using the system traceability. Then we can have a live demo on the same example of HL. Then we can discuss about the future of system engineering. That is what will be the future of system engineering by the year of 2035. Then we can address the queries and we can have a Q&A session. So then let me start with the introduction on digital evolution in system engineering. As we all know that system engineering makes sure that the elements of the system work together to achieve the objectives of the whole system. So this requires the system engineering to deal with the complexity and risk by integrating across various systems like elements, disciplines, and the life cycle. So here the SE can accomplish this by including representation and consideration from each discipline, and each will be affected by the stakeholders. So here the SE guides us the overall technical effort including such as hardware, software, test and engineering. So this will be ensure the solution that satisfies the stakeholder needs and also their expectation. So SEs continue to evolve to support the demands of increasing system complexity and enterprise competitiveness. So looking ahead to system engineering, will leverage the digital information in its tools and methods. It will be largely into the model based using integrated, descriptive, analytical digital representation of the system. So here the system design, analysis and simulation of models, technologies and analysis framework. So these all will be enable rapid design evolution and provide the shared understanding of the system throughout the life cycle. Let me move into the common challenges in system engineering. So here we are facing the different challenges in system engineering. So as one of the challenges for system engineering today is the lot of fragmentation across the engineering tools and data landscape. As we all are working in a specialized areas, each will be having its own tools and data. So integrating all these pieces has become a key to focus, enhance the collaboration to ensure the better analysis. So there are still significant hurdles we need to overcome here. So we are seeing a progress with upcoming standards. For example, the functional markup interface. Functional markup interface, that is FMI, so it is allowing us to improving simulation interoperability, and it's making easier for various tools to work together on a single platform. So on the other hand, we also have open services for lifecycle collaboration, OSLC. The standard is gaining the momentum here for its ability to improve traceability and interoperability across the systems, which is helping to bridge the gap between different tools and data. So even though having these all advantages, many industries still rely on the document-centric process for adopting the system engineering process. To shift towards the digital engineering, it maybe opens up exciting possibilities, but with the new challenges, especially around integrating different tools and ensuring seamless data exchange. So where we also have other model-based standards like system modeling language, SysML, and also unified architecture framework, UAF. So these are all continuing to evolve the better support for model-based system engineering across various systems and enterprises. So in short, we can say that while new standards like OSLC are helping us to integrate tools and data from different vendors and also specialization. But still, we have a lot of work to be done to ensure the system engineering process to keep the needs of the digital age. So let's move on to the another common challenges in system engineering. So, from last 50 years, software has become a vital part of many systems. So, as it has become more complex and interconnected, the software engineering community has adapted by focusing on agility and developments and etc. So, to address these integration challenges, system engineering and software engineers are working together to apply these new methods to cyber civic physical system, so which is aiming to provide better value while managing a risk and societal impacts. So let me move on to the one more challenges. So at presently, the traditional engineering tools and practices are not enough for managing a complex system, which requires a continuous learning and change over the periodic time. So, and these systems implications such as social and ethical implications that need to be considered as a part of a design. So we are still developing ways to ensure the data is fair and that our validation method can keep up with how these systems can make up a decision. So in short, new standards and teamwork are helping us to integrate tools and data better. We are still have a lot to do, ensure our engineering processes can handle the complexities of today's system complexity. So in addition to this, to the above mentioned challenges, specifically in requirement engineering, we find that requirements are written in a plain text and text managed in the Word, Excel, or etc. Or it can be managed in the requirement management tools where the requirement simulation and validation is demanded by the SysML. So it's again challenging to detect the errors at this phase of the life cycle and is also challenging to validate these requirements manually, creating a test cases for each and every requirement and tracing these requirements, and it is challenging to maintain the digital continuity from editors or any requirement management to the next level artifacts such as modeling, design, or any validation tools. With quick introduction to SE industry challenges, we can move on to the digital transformation in SE. So, as system engineering is transforming, engineers are increasingly using newer concepts such as model-based system engineering, digital transformation, and also product line engineering. And more domains are adopting system engineering principles, practices, and insights to their systems. So this is true for very large systems such as system of systems and also complex societal technical system. And for very small systems also, it may be a IoT devices and it may be applicable on medical devices also nowadays. So engineers design and operate a large constellations of small satellites to a planned mission to the Mars. So nowadays, the engineers are developing a new vaccines and addressing the climate changes also through system engineering. So they are adapting system engineering to their practices. So the art is evolving rapidly because of ongoing technical advances and the convergence of system engineering with other disciplines. So next, we'll move on to the case study of automatic headlight system example. So in the system engineering practices, we have a lot of tools, but today we are narrowing down it to a modeling and simulation using SysML and also requirement in loop simulation using real simulation, then to the system traceability using requirement tracing. So then now let's move on to the case study where we try to understand that how we can make sure use of SysML language and diagrams of SysML, then capability of modeling, real and system traceability. So here we have an example of AHL which consists of two inputs. One will be a switch and light intensity. From the figure we can understand that from switch we have a three conditions, that is off, on and auto, and the light intensity will be ranges from 0 to 100%. Based on this input condition, the headlight will be in the off state or will be in the on state. So here we have defined the 3 to 4 requirements for this HL system. So here, but how do we ensure that the specifications are correct, consistent, and complete? So the requirements here are captured by text to ensure that we can move to next slides and we can see it in the demo. So in the first two phases, requirements and architecture defined for a AHL using a SysML tool, that is model built for AHL using SysML modeling language, and the same model data is reused for simulating the requirements for the components to detect the errors and validate against the design and etc. So here the traceability matrix generated for the all lifecycle artifacts. So here we can move into the modeling and simulation of AHL. So in the external perspective, the context model shows what lies outside the AHL system boundaries. And in the interaction perspective, the use case model shows the interaction between AHL system and its actors environment. Coming to a structural perspective, the block diagram or a class diagram shows the organization of the AHL system in terms of components that make up the system and their relationships. And also in the behavioral perspective, the sequence, state machine, and activity diagrams shows the dynamic behavior of AHL system as it's executing here. So the requirements are traced to the model elements. So here you can see that the behavior of headlight is changing with respect to input of the switch. So when it comes to auto mode, depending on the light intensity ranges, it will automatically switch off and switch on depending on the light intensity. So here we can see when it reaches to the above like mentioned range, so it will automatically turn off here. So then we can, now the modeling and simulation of AHL is done. So now we can move on to the requirement in loop simulation of AHL. Before going to a requirement in loop, let's see a main quality criteria or standard safety for functional requirements. So let's dive into the quality criteria for functional requirements. That is what the system must do to operate as expected. So here mainly we have a 4 quality criteria: correctness, so that requirements must accurately capture the system's intended behavior. This ensures that what specified matches and how the system will operate. So next we have a criteria called consistency. So there should be no conflicting requirements. All requirements must align without any collision to avoid confusion and design flaws. And again we have a criteria called completeness. So here we need to make sure that no essential requirements are missing, and every aspect of a system's operation should be accounted for the system. So then we have a criteria called testability. So for this, each requirement must be such that where we can be able to return the test scenarios, and this ensures that we can verify the systems behaves as intended through our simulations and testing. So combination of all these quality criteria ensures that system in the safety critical instance that is mentioned in this figure meet the highest standards by implementing requirement in loop simulation, and also we can catch issues early and improve reliability, minimizing the risk of failure and deployment. So then we can move on to the methods of simulating and validating the requirements. On the slide, we can see that on the left side, we are using a traditional method of manual review based approach, where this method relies morely on the intuition of experienced modelers and to catch issues like conflicting, incorrect, and missing. So however, the relying on this manual efforts to detect these requirement bugs or requirement defects is often time consuming error prone, and also inconsistent. So as complexity grows, the system complexity, it becomes harder for humans to catch every issue, especially across multiple iterations for versions. And also on the better option, we have in right side, we have adapted a requirement in loop simulation. This approach allows us to proactively catch and resolve requirement defects early and saving time and resources by preventing them for cascading down into a later deployment stages. So let's see how the two stimulus help across the two key phases, that is specification phase and validation phase. So at the specification phase, the stimulus allow system architects to simulate the requirements and to detect incorrect, missing or conflicting requirements even before the design begins. So this ensures the high quality specifications early on, which is crucial for the validation safety critical embedded system. So at the validation phase, the stimulus allows test engineers to automatically generate the test vectors and also validating the embedded code complies with these specifications. So in overall, the stimulus saves significant time and effort by ensuring the requirements are correct upfront and tests are generated automatically. So based on these requirements, the seamless approach ensures that both the development and testing teams work more efficiently and deliver high quality validated system faster at the early stage only. So So the stimulus extends the use of models to the detailed behavior which is difficult to capture in the SysML. So in the SysML, we have a requirement diagram or requirement table. So where the requirements are captured in the plain text and not able to simulate. So here the one of the key strength is to of this approach is to digital continuity between the modeling Katayamachi and to the stimulus. So the SysML architecture and the related signals can be uh, architecture can be directly imported to stimulus. So once imported, stimulus enhances the model by capturing the detailed system behaviors where its complex logic and timing constraints or scenarios. So we can simulate and validate the components requirements in the stimulus. So we have a features of stimulus for we can write the requirements in the textual format. We'll be having a standard library inside the tool. We can use of it and we can write the requirements, and also it allows us to create a state machines block diagram. So we can do a requirement modeling and then we can simulate those requirements. And also, as I explained, we can generate a numerous test vectors automatically. So where we can create a scenarios and we can generate test vectors by simulating the scenarios, and we can bring back our designs in the terms of FMU and also our yield test log, and we can verify it against the specifications. And also we have a feature called safety observer. By this feature, we can see the violations of requirement or designs against the specifications. So we have a one more feature that we can export stimulus systems as a FMU and co-simulate with the CATIA Magic tool or any other design tools such as Simulink, Ansyscale, Dymola, and many others. So stimulus export these systems as FMU in the three types. It can be a recompilable FMU or black box or white box FMU. Then also we can import the FMU from any other design tool and also from the modeling. That these things we can show it in the demo. So now we have modeled the HL and the requirements are simulated and validated. Now we have a traceability, like from the word, like from the requirements to a model and model to the requirement simulation and validation. So we have a traceability solution. So here you can see that model elements from the SysML model project and stimulus requirements are traced to the requirements. You can see the traceability graph showing the details such as coverage information from model project and stimulus project to a requirements which is managed in the Word document. And similarly, you can add the various lifecycle artifacts to the rectify project for traceability. So here the rectify tool will generate the traceability matrix and rule violations report and also other various customized reports. So these captured elements can be reviewed and the workflow for review will also be available inside the tool. So similarly, we have other lifecycle artifacts can be added to a rectify project for traceability, that is end-to-end traceability. And these mentioned standards are complied with the system traceability too. So let's move on to the demo. So here you can see the requirements which is managed in the Word document. We have written the requirements for HL system. So now I'll be capturing these requirements in the rectify. So this is the rectify tool. I'm just creating a new project here. Giving a name as demo. So this is the edit window in the rectify. So I'm adding a document to capture the requirements, giving a name as requirements. And type of analysis I'm choosing as a Word. We can choose a file directory. I'm choosing the same Word file here. I'm giving apply. So in the main window, you can see the coverage of requirements. So it is showing the 100%. To add this requirements into the modeling tool, I'm just adding one more document and renaming as CATIA. So here I'm choosing the type of analysis as Magic Cyber System Engineer, and file directory will be a project of model. So then I'm creating a channel from CATIA Magic project to a requirements. So once and click on apply. So in the main window, you can see the coverage of requirement. So till now, we haven't created any relation between the CATIA Magic project to our requirements. So we'll add these requirements into a modeling project. So before that, let me open the model. So here you can see the package requirements. Now no requirements is added here. Let me add the requirements from the rectify. So here I have an option called tools and to add high level requirements. So the same requirements from the Word document, I'll be adding it to a CATIA Magic project. So here I can add requirements here. So it will take a few seconds. Just bear with me. So now we can see the requirements which is added from the rectify tool. So then I'll be showcasing your XML diagrams which I have created for the HL system. So first the block definition diagram. So here I have a main system of HL system. Under that HL controller, light sensor, headlight and switch are decomposed to a main system of HL system. Then we have a use case diagram. So it defines the external actors and the system boundary. So inside of the system boundary, we have created a context diagram where we can see the system interactions, that which signal and which actor is interacting with the system. Then we have a internal block diagram of the HL system. Here we can see the internal communication between the each components. Then for each components, we have defined the behavior using a state machine. Okay. So then let me simulate the HR system using user interface diagram. So here, based on the inputs, the headlights will change its states. So I'm giving the condition as on. So it will change to on condition. When it reaches to auto mode, based on the light intensity, it will be in the on or off mode. So now it is in the 65%. I'll change it to a 95%, 90. So after it will wait for 2 to 3 seconds, then it will automatically turn on. So this is about the modeling of SysML. Then to create a relationship with rectify, that is to trace, we can create a satisfy relationship with any element. So for example, I'm creating it from the block. So here we have a option called create relation. Then I'm choosing the satisfy relationship. Here we can add a requirements from the requirements. So I'm adding a requirement one. Okay. So here you can see that the satisfy relationship was created. So here I'm saving the project. Then if I go back to rectify, it will ask me that if you have modified anything, if you want to reload it. So I'm giving yes. After giving yes, you can see that the coverage of requirements from CATIA to requirements document. So now it is 0%. When I click on yes, it will change. So you can see that it has changed to 11.1. So the same thing we can view it in graphical view also. So here it is from AHL controller block to requirement one. So similarly, you can create a relationship for any other element. Second, you can achieve a 100%. You can achieve a 100% coverage. So now the modeling and tracing our lifecycle artifacts of modeling tool is done. So to achieve a requirement in loop simulation, as I told in the presentation, we can use the same iteral block diagram of the SysML in the stimulus tool. Let me export into a stimulus. So here we have a direct option called export diagram to stimulus. So then you can export it as a XML file. So just I'm choosing a path. Okay. So I've already created. I'm just giving a name as to click on it. So now let me open stimulus tool. So here I'm creating a new project called as test. So here we have an option to import models. I'm importing the XML file which I have exported from the CATIA Magic. So I'm importing. So here you can see the whole internal block diagram and it codes here. And you can just double click on any of the components and you can write the requirements here. And before that, I'm just connecting the ports, creating the signals here. So after connecting, we can see the ports here. So for example, I'm just writing the one requirement using the standard library templates. So I'm selecting the templates one and from logical equals. Okay. So I'm adding a port switch and port headlight. So which will be called as the signals, and giving the input as 0, that is off. So you can simulate a single requirement also, your textual requirements. So here you can see the free graphs that which are the missing requirements. So here we haven't defined the all conditions for HL. So I have already created one project by defining all the requirements. Let me close this project and open that. So here, for better understanding, I have created different versions of requirements. So these are the scenarios. You can see it here. So for switch and light intensity, I have created a different scenarios. The same scenarios I'm using it as an input, and different version we can add and simulate. So for example, we have seen a missing requirement simulation. So I'm adding a version 2. So for version 2, it will create a conflicting requirements. Okay. So that stimulus tool will give you a notification that by saying the requirements are conflicting with each other. You can see it just by clicking on it, you can get to know which requirements are conflicting, and you can modify the requirements again. So here I have a final version that is corrected and consistent. So here you can see no missing and no conflicting, and also no gaps is there in the requirements. So then, as I explained in the PPT, we can generate a numerous test vectors automatically. So this is one scenario for light intensity. So I'm just creating a numerous test vectors by creating a multiple runs, and you can select the steps as many you want. So I'm just giving the 100 steps, and you can see the test vectors generated automatically. The same thing you can export into a CSV file, okay, and you can reuse it in a modeling tool for any other designs. To co-simulate with a modeling tool or any design tool, we can export the system as FMU. So here I'm exporting the HL version 4 requirement and the violated observer to FMU. So from here you can export as a FMU. So I'm exporting as a black box FMU. So now the FMU is exported. So the same FMU, you can reuse it in the CATIA Magic model by importing the option from import from FMU. So I have imported and modeled this comparison of behaviors of modeling tool and requirement tool. I have created a one more project. Let me open it. So from here, you can do a black box simulation as it will run the simulations in CATIA Magic model. For white box simulation, it will take a stimulus as a client and it will run the simulations over there. So for that, I'm just closing the stimulus tool now. Okay. So here you can see a black box. We have made a setup such as for comparing HL controller behavior and also the requirements, that is corrected and consistent requirements with the violated observer. So let me simulate a black box. Okay. So you can see the simulations graph. So we are not giving any inputs manually to the simulation. It will automatically take from this Excel sheet which we have exported from the stimulus, the text vectors. And you can see that passing of vectors to a FMU, from the FMU to the controller. And once, if any violations are there, this observer will turn into a true, so that you can modify your requirements. So it will generate the results in the terms of CSV or Excel. So by seeing that results file, you can modify your design or requirement. So these all are using the simulation configuration feature in the CATIA Magic model. Let me increase the animation speed. So at some point of time, the observer will turn into true. Here you can see. So here now the observer is turned into true. So the same thing will be executed as Excel and you can see it there. So let me pause this and run the white box simulation. In the same way, it will take the test vectors from the Excel file and it will open the stimulus as a client to run simulations over there. So I'm just running it. So here you can see the simulations. So now the modeling tool will act as a server and the stimulus will act as a client. So when the observer will turn into true, so this observer and requirement coverage, we can see it in a requirement tool. So this is how you are ensuring your requirements which are validated in the simulation tool with your behavior or with any other design. So once it turns to true, this green observer will become red observers. So you can see the observer violations and the coverage of requirements, and also it will give the message which requirement is violating the behavior of the system. So this is about the core simulation, and also you can see the results which is generated from the CATIA magic. Okay. So now the core simulation between stimulus and CATIA magic is done. So let me open a rectify to trace the behavior of stimulus. So I'm taking a new document and giving a name as stimulus, type of analysis as a stimulus, and steam PRJ file, that is stimulus project. And I'm creating a channel from stimulus to requirements. So here you can see the coverage of requirements. So I'm navigating a stimulus project from the rectifier. You can navigate any other project from the rectifier directly. So as same as creating a satisfied relationship in the CATIA magic, we have a option called tag in the stimulus. So if you add a tag for the particular requirement, so the coverage will be displayed in the rectifier. So we have a one more option for importing FMU also. So you can import FMU in the stimulus and you can do the simulations. So before that, I can show you the complete coverage of the rectifier. So I have already created project. So here you can see the 100% coverage of CATIA to requirements that is managed in the word file, and from stimulus to the requirements, and parallelly the all lifecycle artifacts whichever we have used here. Okay. So this is about the demo. Let me go back to the PPT. So now we have overcome the challenges such as requirement simulation and validation, and also modeling the AHL and managing the traceability of all the stages. So what will be the future state of system engineering? So we'll discuss on this. Sorry. By the year of 2035, the system engineering will address the challenges through variety of new and emerging practices such as advanced technologies like AI, communication technologies, and etc. And it will impact the nature of the systems, how people will interact with the systems, and the way systems develop. So these technologies will help to deal with increasing system complexity, and the future of system engineering will be more model based and enabled by the digital transformation, and the advanced digital technologies and model standards will enable rapid explorations of designs using high fidelity simulations such as data visualizations and also semantic web technologies. So the and also cloud-based virtual global collaborations leverages the cloud-based high-capacity compute infrastructure and supports massive simulation. And the system engineering tools will benefit from the internet connectivity and knowledge representation to provide seamless exchange of information with the other disciplines and also with the other tool environments. So these connected models are updated in the real time, and the SE tools with AI capability will allow system engineers to focus more on their time on the creative tasks and less time on the routine tasks. So the tool guides us for generating high quality specifications and also design. So the human system integration practices will become essential to design smart systems, so which can be interact effectively with the humans. And also system engineering will leverage the practices from other disciplines such as data science to help and manage growth in data. Formal system engineering theoretical foundations will be codified, leading to a new research and development in the next generation of system engineering and also methods and tools. So there will be a large step to a change in system engineering, that will be education starting with early education with a heavy focus on lifelong learning, and also greater number of small and medium enterprises that will accept system engineering and continues to adopt the manage and system complexity. Yeah. And to summarize the whole webinar, the system engineering is going to continue evolving to support the demands of increasing system complexity and also enterprise competitiveness. So traditionally, engineering tools and practices are not enough for managing complex systems that learn and change over periodic time. So by 2035, the system engineering will address the challenges through variety of new and upcoming practices, and also advanced technologies like AI communication will also integrated with the system engineering. And the mentioned challenges, that requirement challenges and modeling challenges, we have overcome by using a tools called CATIA Stimulus from Dassault for real simulation, and also CATIA Magic tool from Dassault for modeling, simulation, and analysis. And for system traceability, we have used the tool CATIA Rectify, and we have derived some content from System Engineering Vision 2035 from the infos. Any questions?
Thank you, Divya. It was wonderful. There are a few questions. Let me take up the first one.
Okay.
The first question goes like this: how to import requirements from IBM doors and Excel document to CATIA Magic tool?
Yeah, we have a direct integration with IBM tools and other requirement management tools in the CATIA Magic. We have an option called tools. So from there, we can directly import, and also we can import it from an Excel document also directly. We have a direct integration.
Thank you, Divya. There is another question.
Okay.
How test vectors are generated in Stimulus?
Yeah, as I already demonstrated in the demo, just for we need to create a test scenarios first. After that, just we can simulate by using the play button. We can generate up to certain up to certain limit we can generate. It's up to 1 million, I guess we can generate.
Thank you.
Yeah.
So let's take a last question for the day, and we'll answer the rest of the questions after the session, maybe offline, since we are already 10 minutes delayed. So the last question for the day is: can we import MathWorks design in Stimulus for verification against the requirements?
Sure. We can import in the terms of FMU. We also have a option called importing FMU. We can import FMU from the MATLAB or any other designs. We can test it against our specifications. It is possible.
All right. Thank you so much for answering all of these questions on this wonderful webinar. Thank you, team, and thank you, audience, for joining this webinar. So if you have any questions, you can write us on my email address, which is reflecting on your screens right now, and we can take it up from there. Thank you so much, and have a wonderful day. Bye-bye.